Good afternoon, everybody. Thank you for being here. My name is Carlos. I'm CEO of Matera. We are a fintech company. We provide software for banks and fintechs. I'm here much more because I'm the CEO. No? I have here Bruno Samora, my CPO for the company. He knows better the product than I do, so if you make any tough questions, I'm going to ask help. No? So next presentation, next event, probably going to ask some architects from the company to be here instead of myself. I enjoy very much show. Much more deep tech than I thought, but let's go. So I'm going to talk now about event-driven architecture, that is a solution named Digital Twin. And I want to tell you how we scaled this up, how we could survive a very challenging environment I'm going to describe to you. So what's the Digital Twin? Maybe who have heard about this before? Digital twin for banks, not digital twin for industry, for manufacturing plants. Nobody, good. So that's a new concept we created. That's a kind of solution for this problem. Legacy banks today, they are not 24/7. They are batch-oriented, they sleep every night, they stop during the weekend, but real-time payments are 24/7. So I want to pay 3 a.m. in the morning, I want to pay Christmas Day, I want to pay any time. I want to pay for my beer. I want to pay. So, and it happens in Brazil. We pay any second. There is no bad day for a bank. It's 3 a.m. in the morning, Sunday, I don't care. I pay. I can transfer money from bank to another bank. I can transfer money from my bank to Coinbase and buy Bitcoin in 30 seconds. That's the reality. So how to solve this problem if the real-time payments are 24/7? Stable coins are also 24/7. We are 24/7. We love coding during the night, but the core bank is not. There is a gap here. Replacing the core bank is a good idea? No. Replacing the core bank in general causes the CIO to get fired. 5-year projects that's going to 7-year project, a lot of money, and we know a bunch of core replacements that failed. Just use a lot of money from the bank for nothing, no results at all. So every CIO is afraid of replacing core banking. So we have a challenge here. 24/7, I'm afraid of replacing my core bank. What do? Retire? That's an option, right? But we create here a write-back cache. So it's an event consistent solution that's digital twin. So I have here, I'll let you get the point, the laser point. I have here digital twin as a kind of write-back cache on top of the legacy. So we put all the digital channels talking to digital twin, not to the core bank anymore. RTP, FedNow, stablecoins, all coming here. And the debit card coming here too. You don't need standing solutions anymore. And whatever happens here goes here. Whatever happens here goes here. So if this system goes down, no problem. Nobody's going to see that. As a user, you're going to keep using. Who here remember the day the Capital One was down for the day? For a complete day. It was on the taglines of the press. The same day, one client of Matera's was down to. No taglines. Nobody knows about that because they were using this. So the core bank was down, but the users we are using. I remember when I was informed about the problem, I transferred money to my daughter. No problem. From my point of view, the bank was up. So by creating this layer, we create a piece of software that keeps the user happy, not the regulator happy. The SLA here is seconds. SLA here is days. I can transfer the file to Fed or to OCC, whatever, by the end of the month. If I delay a little bit, just a fine. But if I go down here, I'm going to CNN, talking that my bank's off. And people get afraid of that. People miss dates to pay bills and so forth. So it's a huge problem. So why to put all in the same software? Why not to put in a software just to keep the user happy and live here? So there is eventual consistency between these two guys. Cannot be strongly consistent, of course, because for strong consistent means if this guy is down, I have to be down again too. I don't want to get down too, so I want to be up. So it's eventual consistency by design. And no double spending assured. We solve the problem because you guys know when you have eventual consistency, eventually I got $5 here, I got $5 here same time, and the account balance was just 6. I use $5 twice. So this problem is solved here, so you don't have double spending. And it's super fast, super resilient, distributed, like you can have one digital twin in Amazon Web Service, you can have another digital twin on Google, you can have another digital twin in Azure. And what you do when Amazon is costing you too much? You beg for a discount, right? With digital twin, you just shut it down. And you go to AWS and say, okay, what's the price to get it back on? You don't beg for discounts. You just shut it down because you have other instances of digital twin in other cloud providers. So it's super resilient. It runs on, in AWS, it runs on Graviton, ARM CPU, so it's very fast, very cheap. And today we process those of 1,000 transactions per second in a lab, not in real life because we don't have this volume of transactions there. But it was tested by Accenture, and we did it. So it's a very fast ledger that can, by just being added on top of the legacy core banking, we solve this problem here. And let's show the challenge. That's in Brazil, where we come from. That's the volume of Pix transactions, Pix instant payment transaction like FedNow. Look how it grew. So, what's happening here? Oh, back. So as you see, from 0 to 1/3 of Visa does worldwide in one country, not worldwide, after 4 years only. So we launched this product, and like a month later, we were doing like 40 million transactions in one country, in one client. So, and when you do transactions, what's an instant payment transaction? It's just a distributed transaction. An instant payment is a debit in a ledger and a credit in another ledger. And the messaging between these two ledgers are just messaging to assure is going to be an ACID transaction. So that's instant payments. It's a debit and a credit in two different ledgers. So if the ledger is low, the instant payment is low. If the ledger takes too long time to process one transaction, the transaction time is out. I'm not sure if you know, but guess what's SLA for this transaction in Brazil? How many seconds I have to process each transaction for this volume? Who gets the number here? I'm going to tell 6 seconds. If you do, you have to make an average 6 seconds. You can go to 10 seconds for a very small percentage of your transaction. After 10 seconds, it times out. So if the ledger is low, all your transactions are going to time out. You don't process. So when you talk about instant payments, everybody talks about the messaging, ISO 200, whatever, but the ledger plays a fundamental role. The instant payment is the airplane, but you need the airports, and the ledger is the airport. So that's why this is a big challenge. You need a very fast ledger to support this volume of payments. In India, they are doing more transactions than Visa worldwide already. So this kind of pay-by-bank transactions are killing credit card processing in the world. Probably is going to be the new era for payments. It's not going to be a card anymore. So let's talk about the solution. How we solve that. These first 2 slides much more to put you in a context. Why in the hell I'm doing this? So let's talk now about how we made this happen. So we're going to talk about the topology. We thought APIs. We believe that we, as a community, we use too much REST APIs. We skipped. We're not using just REST APIs. For some problems, REST APIs are not good. I want to talk about this. And KEDA scaling, that is, we're going to scale not based on CPU consumption, not based on memory consumption, but based on business demands. So we're going to forecast business demands. You're going to see the size of topics on Kafka. Then you're going to auto-scale the Kafka based on business decisions. And I'm going to talk about the out-of-box pattern that's very specifically used here. When you go to this guy here, sending transactions to digital twin, Outbox is a pattern that you're using here to assure that a very old system is going to perform as fast as possible to transfer data in binary mode and compacted by zip. So it can be faster. And we tried before, not doing this, it failed. We had a lot of problems in the previous generation of our software because we didn't use Outbox. So we learned from the worst way possible, by failing. So this Outbox pattern is very important to be used. So, sorry, I have to read here. So basically, we're not going to talk about just infrastructure. For this volume, it's not a matter of adding big servers. We're talking about volumes that big servers are not enough. You have a latency, you have bottlenecks. If you have a bad design system in a huge machine, it's not going to work. It's not going to survive. You're going to time out transactions. So to do this, we invest a lot of time in the design of the solution to be capable of running. We start digital twin after peaks. We start peaks with a second generation of ledger, then we move to the third generation, that's digital twin. Okay, and we use a lot event-driven. So we use Kafka there, and Kafka is supporting very well. If you heard about problems with Kafka, Kafka is supporting today even hedge funds in Chicago. Actually, they were not supporting very well, but this hedge fund, a friend of mine working there, he solved the problem. He improved the Kafka, he returned, so the Kafka open source available for us is red contains this improvement. But for payments is enough, more than enough. So it's we are very happy with Kafka for this. And we synchronize between two databases using Kafka. We don't use database to synchronize. So we work on different databases on different nodes. So if there is a bug in one database, we have another database to survive. So we're resilient even to database bugs. Because if you have a cluster where we have a single database controlling all the cluster, if that database fails, your entire system will fail. So we don't use the same database for all nodes. We use different database at the same time, and we synchronize them using Kafka. Everything is event-driven. We have an event here. That event will replicate to other nodes, and other nodes process those events. So another thing, we have situations on real-time payments where we have very challenging peak demands. When they show that graph, like doing 7 billion transactions a month, it's 7 billion a month. If you divide by the number of seconds of the month, you don't have exactly what you process. We process much more in some seconds. Like if you have Amazon Prime Day, or any Black Friday, or big payouts, like payroll day, in situations like these, you have very huge peak demands. Or, for example, a bet sport in Brazil is very relevant, and when a game is happening, everything goes up like crazy. It's worse than Prime Day. When there's like two soccer teams playing to each other, and there is people betting there, and to bet they pay off picks, the transaction level grows like crazy. So, and from nothing to tons, from 1 second to another second. So you cannot just react to an autoscale if the system goes down because there are too many transactions. So you have to survive that. That's why we thought about surviving this kind of burst capacity and peak demands. Latency is very important. We fight latency the best we could. A lot of programmers, they forget about latency. Like latency does not exist. Latency exists. And even if we talk about milliseconds of latency, when you have 7 billion transactions a month, for milliseconds of latency kills you. So we have to fight every kind of latency. We have a lot of regulatory stuff that have to survive, like receiving credits that should be blocked before releasing, or racing conditions like the judge asks us to block $1,000, and the person will receive $2,000, and we cannot be pulling the account. When the money is received, you need to block immediately. So we cannot be pulling. So we create solutions to survive these regulatory demands where the money is coming, we block. As the money comes, Also, we thought about in the beginning that, okay, we're developing a new solution for PIX, but crypto is coming. Why the hell am I going to create a new solution just with 2 decimal points? So this ledger is multi-currency and multi-decimal point and multi-time zone. So today, we're the first banking technology provider to make a partnership with Circle to control balance, off-chain balance of stablecoin USDC as well. Because USDC, I'm not sure if you know, but they have, USDC has 6 decimal points, not 2. And we're good to go. We control any number of decimal points. And use this event streaming, for real-time flow. They're going to show here. And we do a lot of CPU optimizations to save, well, a lot of our code were very tuned to save memory, to save CPUs and so forth. And they're using memory optimizations. We're using, of course, SSDs in the server. And we are fighting network latency too. We avoid too many round trips between servers. We do micro-batching a lot, because when you do micro-batching, you fight latency. So talk about traditional REST APIs. Every time you make an API call, REST is a single API call. You have to wait for a response. Imagine you're having 1,000 transactions per second. Every 10th of second, you have 100 transactions. Why are you going to make 100 API calls? You can wait 0.1 seconds. It's only going to kill that 6 seconds time frame you have. But when you wait 0.1 second and you keep all the transactions on Kafka, and you look at the Kafka, you're going to see 100 transactions. If you have 100 transactions, you can make one database insert with 100 rows. So we don't make 100 inserts with one row. We make one insert with 100 rows. And one insert with 100 rows is almost the same cost of one insert of one row. So it's 100 times faster. And imagine those 100 credits are for the same account. Amazon selling like crazy. Why am I going to update the balance 100 times? I can update the balance in just one time. So we can make transactions in parallel. If I wait 0.1 seconds for every, just look at the Kafka, and my API is event-based, people are posting transactions on Kafka. They're not calling REST API directly to my system. I can take 100 and process at the same time. And if it comes to 10,000 per second, I get 1,000. And when I insert 1,000 rows, it's almost the same cost of inserting 100 rows. So that's why our solution, when we make stress tests on this, the more transactions you put on the system, faster it is. Because the system has more chance in a window of 0.1 seconds to get the largest amount of transactions. That's possible because you're not offering to our users a REST API, you're offering a Kafka-based API. So they're just posting messages there on the topic. So we look at the topic and we process the topic. And we have to analyze everything that's coming there, if it's the same account or for different accounts. So when it's the same account, we can aggregate all the amount and make just one update. And this piece of the software is very critical because authorizing transaction is critical, as I showed before. After this, we transfer on Kafka topic to another database. That's where you query your balance. That's where you query your recent transactions. So we separate one database just for transactions and another database just for you to query balance and transactions, the recent transactions. The database for transaction, the database just do this. You can even use a NoSQL database if you want, because it's just a proof transaction. This database does nothing else because you have to protect this database because it's more important database you have for ledger. That's what you do to make this happen. We use API REST, of course. We use like if you create a new account, if you create a new currency, or you're gonna say shut down this account, that's okay. But for transactions where you have the volume, we have an API, REST API. So if you don't need too much volume, you prefer easy way to use, you call REST API. But if you have volume, you have an option to use Kafka and post messages there. Another thing, we don't use JSON, we use Avro for Kafka. So it's all binary. We don't waste CPUs converting binary to string and string to binary again. You know, so we use Avro. So by using Avro, you save a lot of CPUs. It saves money too, because one question they ask to me all the time is how much a transaction costs. So if I'm using, we are costing less than 1 cent per 6 transactions in Amazon. So AWS, the problem is how much I'm going to pay to AWS per transaction to run your software. So if your software is not efficient, you're going to make Jeff Bezos even richer, and just by making efficient code. So with this software, we're using ARM CPUs in AWS and make this very optimized. We can save money for our client on AWS. So it's not only what they pay to us, it's what they pay to AWS. And by doing this, we can get a little bit more, because you can say the total, even if our ledger is a little bit more expensive than the competition, we save money on AWS, so I can get this money. I can get this better payment. Okay. So by using KEDA to autoscale our solution, basically monitor the Kafka topics to know if it's coming too many messages there. We can see also the legacy system is coming too many transactions. So based on size of queues, size of topics, and so forth, we're going to autoscale the Kafka cluster we have. We don't autoscale the Kafka cluster based on CPUs being used too much or memory is missing, whatever. So we can do this earlier, before the problem coming, because you're seeing the volume of transactions are coming. And even if you have too many messages in Kafka, nothing's gonna, the system's not gonna drop, because maybe it's gonna be a little bit slow, but never is gonna crash. When you have too much calls, synchronous calls, you can crash the system, but using Kafka, you don't crash the system. The worst scenario, before scaling up, it's gonna take a little bit longer to process the topic. Consumer scaling, so that's one thing queue message, like the queue depth trigger. If you have more than 1,000 messages, you have to scale up because Kafka is having too many messages. Or process like thresholds, okay, if it's taking more than 100 milliseconds to process one message, you have to scale up. Partition or scaling strategies. And so basically we see these kind of data points to decide for scaling up the system instead of using memory or CPU. Of course, you watch CPU, you watch memory too, of course. But in general, we scale up based on these methods. And so that's, also we can, those red and green lights enter the highway, right? We can also control the legacy system. If the system's coming to us with too many transactions, but that system can wait. Some payouts, like PayPal doing payouts, they don't need to be a payout at the second. Some users, they can tolerate 10 seconds or a minute or even an hour to process that payment. So we have some lanes where we know that they are not so stressed on time, so I can hold them a little bit. So you're controlling those Kafka topics coming from, depending on the source of the transaction, we can wait. A user on a cell phone, that's top priority. You cannot say, wait a little bit. No, I'm pressing the button now, I want the payment now. I want to leave the gasoline station now. I want to leave my restaurant now. I'm paying on Walmart, I need to leave now. So that's most urgent. But TriNet making a payout can be now or in an hour. You just want your money today, your salary today. Don't need to be at that second. So we can manage those different topics based on the urgency of the payment. And to synchronize the legacy of digital twin is very important, because you talk about a COBOL-based system, Oracle-based system from the 90s, from the 80s, that you have to capture all the transactions that are happening in the ledger of the legacy system and replicate the digital twin. In general, those systems are very monolithic, very tough to manage. So what we did, It was an Oracle-based one. We created a database trigger on the transaction database of the legacy system. So whenever transaction comes, we put a copy on the outbox. The outbox is another table, and you commit the transaction. So we didn't delay the system. We didn't make any API call from PL/SQL. That's going to be terrible. We just kept everything inside the PL/SQL. So the transaction was coming, the database trigger was triggered. Then we insert a row there in the table, the outbox table, and you commit. So it's there. The transaction is finished. Then you have like an agent that's looking at this table like every 30 seconds, every 10 seconds, depending on the SLA you have. And you see there, okay, we have now 200 rows to be replicated to digital twin. So we pull those 100 rows in a single batch to fight latency again. And we put in binary for every row with zip, so we don't use bandwidth on the network, and you push to Kafka. So when you push to Kafka, digital twin is going to pull that message, and digital twin is going to say, okay, I have here 100 transactions. Then you do that micro batch again. So the way you replicate the data from the legacy system to digital twin using this approach with Outbox is very important. It saves our life. We tried before using row by row. We faced situations where the system was like 1 day later, 1 day behind time, because too many transactions coming and latency, one row going and getting back, another row going and get back. So all that latency involved in the communication between these two systems, it killed the system. We could not survive. But with this micro batch stuff on the Outbox machine pattern, we could make all the transition between the legs and digital twin in like 10 minutes, 1 minute. It's very fast. So it's very important this approach you used. Of course, you depend on the legacy system you have. Thanks God this one you used was an Oracle-based at least, but you have other systems based on COBOL, no database files. No database, if there is some core banks, they don't even use SQL database. They use flat files. So I don't know how it survives, but it is what it is. So depend on the core bank, you have to find the strategy to pull those transactions and create this outbox pattern that's going to be one by one. There is no one-size-fits-all solution, okay? So by doing this, we assure that we decoupled the transaction side of the core bank, the legacy core bank, with the replication. So the transaction does happen there. And if the core bank goes down, no problem, because it's as the transaction side, the legacy database. If the trigger fails, we're not going to insert. Once you commit Oracle, that commit is going to assure that the transaction happened and the outbox row is there. So it's very resilient, and the code that's going to be pulling data from this table and publishing to Kafka is a new code you just create, so it's resilient too, and you assure the delivery. And by using Kafka is very important because Kafka assures the order of the messages. We had problems using all other messaging queues before, like you were opening an account, then sending transactions to the account, but the queuing system inverted. So you got a transaction to a non-existing account. Or an account that had an overdraft limit, they raised the overdraft limit, there was a debit, then they reduced the overdraft limit. And if you invert the order, you can reduce the overdraft limit, then come the debit. And you cannot process that transaction because you don't have overdraft limit anymore. So assuring the order of the transactions between the legacy and digital twin is very important. And Kafka assures this order of transactions, okay? So here's an example. This 1, 2, 3, 4 are examples of we do microbatch here, and also there are events here that you have to respect the order. If you don't respect the order, it's not going to work. And you use, I believe, SQS before, and they messed up with the order of the messages, and we had problems. So most of this solution I'm showing to you, it costs a night of a non-sleeping night for sure. Like when I remember until now when we had this problem with a debt transaction that happened in the core banking, and digital twin was refusing. And why and how? You're cash. How can you refuse this transaction? because it was inverting the order. So I have the producer there producing the messages and send on different partitions, and everything goes to zero twin. So it's a kind of a Dropbox of legacy day systems. And key takeaways here, architectural decision, we put top priority on event-driven, instead of synchronous APIs, especially for transactions. If you do transactions with synchronous APIs, you're going to have a big bottleneck, you're going to have latency, you're not going to survive the demand of 6 seconds transaction between two banks. Of course, like I said, we have. This outbox was very important. The previous generation, we did not use this. It cost us almost a client, a lot of big problems. This KEDA for predictive autoscaling is very important to us. It helps us to survive with, we don't need to oversize servers. We can work like as low as possible, so it saves money for the client on the cloud provider. So by monitoring this, and of course we have some plan for some demands we can advance, but it's still KEDA. You can forecast based on, if I have an API that's going to tell you about a soccer game that's coming or a football game that's coming, there's going to be a sport betting, you can autoscale based on business activities coming. You don't need to use to see just the topics on Kafka. You can see some other source of data that can forecast peak demands. Then you can, and sometimes it's manually. Sometimes like Amazon announced that tomorrow is going to have a Prime Day, and they gave a 10% discount for paying peaks. So we can, everybody's going to buy midnight paying peaks. So let's make more servers here. Basically that's it. The success is very good. So I'm going to go to questions here. And please. Yeah.
Thank you for the presentation.
No, very bad.
We also had, I think, earlier today, this from your colleagues from Brazil, from Marian. From ground up, and we can see the crazy performance. So in US, we don't have the government-mandated real-time payments. What do you think can be the catalyst for this to happen? Because banks are not really interested. It's a huge overhead for them. They're losing money on the exchange. So what would change?
Educating them. They're going to be making more money. Actually, it's going to change. Have you heard about X9 QR code? X9, we were there inside X9. That's a credit organization by ANSI. So it's going to be the official QR code for the United States. We made some analysis. You know that debit cards in the United States are capped, right? The interchange. The bank cannot make more money than X cents per transaction. This regulation doesn't apply for pay by bank. So if the bank starts paying on FedNow, they can make twice as much. So that's a trick. You don't need the government mandating banks if they can make more money on top of this. So this X9 was the bank that helped us to found this is Wells Fargo. If you see the webinar where we're demonstrating X9 working, Wells Fargo was there. And that's a public name. You have US Bank there. I can't remember other banks, but I cannot mention some other names. But top 4 banks in the United States are supporting us a lot. So basically, and for those volume of PIX transactions in Brazil, 53% are QR code. So we talk about in the United States going to 3.5 billion transactions a month, maybe in 3 years, because there is money on the table. And we're going to start on bill payments, not paying stores, because for us it's okay paying stores. You tap your phone and you leave. That's nice, right? Behind the scenes, there are huge costs that you can be able to solve. But it's more challenging to convince the user to change the behavior. But to pay an invoice is a pain in the ass. Unless it's auto debit, it's very complicated. So we're starting on invoice. And we have big billers already committed to put this QR code on invoice. And once you have big billers, big banks they are visiting Brazil in 2 weeks to know this. And probably every big bank app in the United States is going to be scanning this QR code by the beginning of next year. So by having a big company invoice with QR codes and our top 10 banks or more is scanning this QR code, we're going to see this happening. I'm not sure if it's going to be Fed now because their X9 is rail agnostic. So our game is the cheapest is the best. So it can be Solana, it can be Polygon, it can be whatever. So the idea is you scan the QR code and you push the payment. There is no credential, there is no credit card numbers, there is no card numbers, there is no secure element. And for stores for the future, we have a solution for tap to pay. So you get your phone, you tap, you confirm and leave. But when you tap to pay, you don't send to the terminal your card number, not even a tokenized card number. You send 0, you send nothing to the terminal. The terminal tells your phone where you have to push the money to. Then you push the money using any rail to the payee. So with X9, it's not just a QR code. It's actually a payment request format for the biller or the merchant to request a payment. Today, when you tap a card, you say, merchant, you can grab from my account any money you want, and they trust you that you're going to get just the amount on this screen. So you're trusting the third-party terminal screen. And you type your PIN there, you're trusting that keyboard with your password. It's bad by design. With this QR code, you don't trust the terminal of the merchant. You trust your own phone. You scan the QR code, you tap, your phone is going to pull the data. It's digitally signed by the bank, so no QR code swaps. And you see the data, you confirm on your phone, then you push the money. And the merchant receives the money. And the merchant says, thank you. And the merchant don't have a clue about your card number. The merchant don't have a clue about your account number. So with this, I believe it helps answer your questions. What happens? We're going to eliminate all the middlemen. Everybody in the middle. Who's going to make more money? Whoever survives. Banks. Who have a payer bank and the payee bank. They're going to make more money. Simple as that. So that's the reason for them to engage, because they prefer getting the pie just for themselves. And nobody's going to eat any slice of this pie anymore. So that's why. And they were, it's impossible, it's not good, but it's happening. UPI, more transactions than Visa worldwide, just in India. PIX, Thailand, Australia. So it's going to happen. And banks are going to make more money. There is money on the table. So that's the mandate, make more money, Welcome. Any other question? Okay, guys, that's it. Thank you very much for your time.